A common rule of thumb, one token is about 4 characters in English, roughly 3/4 of a word, useful for intuition. Training at this scale requires specialized hardware like GPS or TPS, designed for the tensor operations deep learning relies on. Tensors are multi-dimensional arrays that represent data and model parameters. Most training is large-scale tensor computation. Early generative models use recurrent structures that process sequences step by step, carrying state through time. RNNs can model sequences but struggle with long dependencies because learning signals can fade or explode during training. With long sequences, gradients may shrink, making it difficult for the model to learn relationships between distant tokens. LSTMs introduce gating mechanisms to preserve information longer, improving performance on sequence tasks like generation and recognition. Transformers replaced recurrence with attention-based layers, enabling parallel processing and stronger long-range dependency modeling. The transformer's core is attention. It dynamically decides which parts of the context to use when building representations. Many transformers use an encoder stack, a decoder stack, or both, depending on whether the task is understanding, generation, or both. Encoders transform input tokens into context-aware representations, often used for understanding tasks like classification or retrieval. Decoders generate output tokens autoregressively, using attention over prior tokens to produce fluent continuations. The decoder predicts the next token, appends it to the context, and repeats. This loop produces full text outputs. Because attention is not inherently sequential, transformers add positional signals so the model understands token order. Multi-head attention runs several attention mechanisms in parallel, letting the model capture different relationships at once. After attention, feed-forward networks reshape representations nonlinearly, helping the model learn complex mappings. Residual connections and layer normalization improve gradient flow and stability, enabling very deep transformer stacks. If you need generation, chat, or writing, decoder-style models are common. For representation learning, encoder approaches are typical.